Hello everyone. So today we are going to talk about one of the very important topic of signal processing, that is Fourier. Fourier, which is one of the analysis and synthesis tool. So before we start, can you guess who these three are? Right, so I'll answer for you. This person on the right is Fourier, of course, because we are going to talk about Fourier in detail. This is Laplace, who was actually guide of Fourier, and he submitted his thesis under Laplace. And of course, Laplace transform is related to Fourier transform. It comes from Fourier transform, so that's why I'm talking about this. And this guy is Newton, Sir Isaac Newton. Sir Isaac Newton is actually one of the very great mathematicians. That's why I'm talking about this. Alright, so let's talk about the Fourier. So if we start with the Fourier, let's talk about something about the Fourier's history, how Fourier series came into picture. So history of Fourier started in 1748. In 1748, one of the mathematician, Euler, he was working on the vibrating string. Vibrating string means he was working on a string that if this is a string bounded on 2 points, and if you plug this string, it will start vibrating, right? So he was working on this vibrating string, and he said that deflection, you can see simply that this deflection, if I consider y, this is different at the different point, right? And if you plug it, after some time it die down. So he actually said that this deflection is a function of two things, which is one is x, which is a distance from this point. You can see at 0 it is no deflection, at complete L it is no deflection, and at this point it is maximum. And a time, after a certain time this deflection goes down, right? So he said that we can calculate this, and he said that this can be composed from some normal mode, weighted normal modes. So he said that okay, this is the first mode, this is the second mode, this is the third mode, likewise, right? And he said that we can calculate this from some weighted sum of these three things, right? And in 1753, Bernoulli, he argued on same thing on physical ground, but no mathematics was included. That's why this was not accepted, and even Euler himself discarded this trigonometrical series idea of Bernoulli, right? In 1759, Lagrange, another mathematician, he strongly criticized this concept of the trigonometrical series, right? Now you can see history started in 1748, and Fourier, who was born in 1768. He was born in very small village of France. He was mathematician, Egyptologist, first Egyptologist actually, and he had a revolutionary discovery, which is actually Fourier transform, which actually changed a lot of subject. If there would not be Fourier transform, we might be studying this course in different way, right? His discovery came in 1822, and he died in 1830. He was also scientific advisor of Napoleon at that time, right? So let's talk about his claim. He gave two claims. One of them was this. He said, this was his claim, he said that any periodic signal, right? For mathematician, signal is function, right? So any periodic signal can be represented by a series of harmonically related sinusoidals. So let's see that what he's saying. He's saying that let's consider x of t as a periodic signal. Let's consider that this is a periodic signal with period of t naught, which you can of course write by the 2 naught by omega, 2 pi by omega naught, right? He said this can be represented by a series of harmonically related sinusoidal. Now what do you mean by sinusoidal? sinusoidal is e to the power j theta, right? Or we can write this theta as omega t, right? So that this is sinusoidal, I should write like this, right? So he said that we can write a series of harmonically related sinusoidals. Now what's the meaning of harmonic? Harmonic means that, let's say, if there is a function 1 which has frequency omega naught, and there is if another function with frequency of twice of omega naught, and another function which is k times omega naught, and these all are, and where k is integer, these all are called the harmonics, right? Now he said that we can decompose this in harmonically related sinusoidal. That means I can write this as series of this harmonics with, of course, in place of theta we will have omega naught, right? So I can write this plus the next harmonic of this would be this plus 3 times omega naught t, and of course so on, not only in positive but in negative also, omega naught t minus twice of omega naught t likewise. And here I left that to write that minus 1 1, so it would be again 0 times omega naught t2, right, which would be 1 actually, right? Now if you look at this expression, this complete series, there is nothing different. You can calculate every value of this just by plugging this value of omega naught, and that can be calculated by omega t naught, right? So what's the difference if there are two different functions of this function with the same, let's say another function with same periodicity? Then can we write the series of this in terms same for this? No, so there must be something different. So difference is that this series is not just a series like this, there is some weighting coefficient, like something which actually is multiplying by this factor. So he said let's multiply a to everything, right? Now a cannot be same for everything, so he made a name, he gave a name to everything. So it is of twice, so he said a2, 3, so a3, 1, so 1, 0, so a0, minus 1, so minus 1, minus 2, so minus 2, and that's coming again, and I'll write that again. So I'll write now in compact form. So he said x of t, which is a period of t naught 2 pi by omega naught, can be represented by, I'm just writing that complete series in compact form, ak e to the power j k times omega naught t, and where k comes from minus infinite to infinite, so 0 would be also there, 1, minus 1, and all value. And he said this is nothing but your Fourier series, right? Now question comes that if you know this, he said that if you know this, you can calculate this very well, right? But what about this? How to calculate this? So this is the only thing that we calculate in Fourier series, right? And the formula for that comes from the derivation. We will not see the derivation, but I'll tell you the analogy. Always look at this analogy. We are going to calculate this. This comes there, and this value comes here with the integration. Now because this is a periodic, you are not going to calculate integration over entire thing, but over t naught only, because it's a periodic. 1 upon t naught for normalizing factor and complex conjugate of this, so that becomes e to the power minus, it becomes minus j times k omega naught t dt. This is the way that you calculate Fourier series, right? Just remember, I'll come back to this, right? So that's the Fourier series. Let's talk about now Fourier transform. This Fourier transform that not only just a periodic signal but also a periodic signal can be represented, but not as a weighted sum of harmonically related sinusoidal as it is in this, but a weighted integral of sinusoidal that are not at all harmonically related.
Okay, I'll write here. So in Fourier series he said that if x of t is periodic with period t0, it can be written as a summation series of ak e to the power j times k times omega naught t, right? And where k comes from minus infinite to infinite. And for Fourier transform, he said that this, when it is not periodic, it can be written in terms of some not discrete coefficient, discrete number, but a continuous number. Let's call that a omega. It's not a discrete variable anymore, it's continuous variable. So we cannot do summation for discrete variable, we will have to do integration, right? And again the same analogy, e to the power j times, now there is no k because this itself is a continuous variable here, dt, and now this integration is over t omega. Why? Because this is in time domain, so it cannot be over t, right? And there is one multiplying factor for this. This factor comes because of the omega, which is omega is equals to 2 pi f, right? Whereas if we write it in terms of f, there will not be such term, right? You can write this in terms of f. Right now this is a function of omega, and you can write this in terms of f, and if you do integration over, this will not be, there will not be any 2 pi, right? So this is, he said, is your Fourier, right? And now exactly for this Fourier series, how do you calculate Fourier series? If you calculate starting with the ak equals to 1 upon t naught over t naught x of t e to the power minus j k times omega naught t dt. So similarly for this, you will be writing as a, when it is a function of omega, as not over t because it's never a periodic signal, x of t again. Now this would not be here, so it will be from minus infinite to infinite, e to the power minus j only omega t and dt, right? And for this we know this is that's how you calculate your Fourier transform, right? And this term we actually normally write as j omega, well-known term. So this is your Fourier transform, and this is the way you calculate Fourier series, right? Can you see the analogy? Same thing, right? There's the same, almost similar kind of analogy, right? Okay.
So just to end this lecture now, Lord Kelvin, William Thomson at the time, he said that Fourier series is a great mathematical poem, really. And Laplace was actually guide of Fourier. He initially rejected Fourier's thesis, but then after he not only accepted but generalized Fourier's and made his own transform, that is called the Laplace transform, right? So next we will be talking about some of the question on the Fourier series and how it actually we calculate and we do calculation over the functions, signals and systems.